This is a review of Chapter 10. If you would, you need your book, and open up to page 267, and then come back. On page 267, they start to talk about the ideal spring and simple harmonic motion. You can apply this for springs and for pendulums. Turn to page 268. On 268, equation 10.2, the shaded in box, Hooke's law. Is an equation you should know. The negative, you may or may not need it depending on the problem. But force equals the spring constant times x. The spring constant K tells you how stiff the spring is. The displacement, this is key, the displacement is measured from where the spring would normally be if you didn't pull it or compress it or hang a weight off of it. Okay? The correlation to that in a pendulum with the equilibrium point would be where you would measure from if you're going to think like that. It would be at the bottom. Okay, so a spring is where it's not bouncing up and down. If you have nothing on there, where is the displacement from where the spring is attached? In a pendulum, it's just the lowest point. Restoring force for a spring is Hooke's law. Restoring force for a pendulum, which also follows simple harmonic motion, restoring force for a pendulum is that net force that acts towards the lowest point. Two different setups, extremely similar ideas. The oscillation back and forth, the restoring force, etc. Take a look at probably the most important picture in this chapter. On the bottom of page 269, they have a spring going back and forth and paper being pulled along with a pen attached to it. This is how you go from having something going back and forth in the x to a nice sine wave that we can analyze. You could also do this for a pendulum. It'd be a little bit trickier, but you could do it for a pendulum as well, going back and forth. And if you don't see how this happens, you can't visualize what's going on here, literally have somebody pull a piece of paper by your pencil as you move the pencil horizontally back and forth, and you'll get a sine curve. So on the y-axis, you have displacement. On the x-axis, you have time. Now, why do we want it like this? Because we can figure out all sorts of stuff from a sine curve. Take a look at page 271. Equation 10.5. Just a quick reminder, frequency is 1 over the period. What is frequency? Frequency is how many per second. If you remember when we did sound in physics, it's how many waves come by your ear in a second. Okay? Period is how long it takes to get one wave to go by. So period's how long, frequency is how many per time. Period is how long for one wave. So you can look at a graph and you can figure that out. How long does it take to do everything it's going to do? So you can get period. If you can get period from a graph, you can also get frequency. That's old news. That's stuff we've done before. Now, there's this new thing called angular frequency. Okay, we're talking about radians now instead of degrees. If you look at equation 10.3, you'll see the equation for displacement in terms of angular frequency. It's A cosine omega t. That is something that you need. Okay. That's something new that we're going to have for the test. The other big thing is how do you relate this new angular frequency to the old typical frequency we worked with before? That's equation 10.6. If you know frequency, you can get omega. Okay? In 10.6, it just says omega equals 2 pi f. Just make sure you're looking at the right equation. And the units are a little different for omega. It's in radians per second. So that's how you go back and forth. Okay? And sometimes you will have to go back and forth. If you haven't done so recently, please reread from the start of 10.2 until velocity and then stop. And come back. Okay, welcome back. If you have any other questions on those 4 formulas that were in there, please ask about it because you are responsible for those 4 formulas for the test. The stuff on velocity, you should have read it, the next part on velocity and acceleration. It comes into play sometimes. I don't know if you're officially responsible for the formulas or not. I've seen it in some practice questions, but not on actual released questions. So that's there's a little bit of a gray area there, but still look over it, read it, be familiar with those equations. Okay, the next big thing is for a pendulum and a spring, their period and their frequency. Okay, we've done period of a pendulum before. We have not done period of the spring. Okay, or frequency for that matter. Remember that frequency and period are related. It's just 1 over. Just take the inverse to go back and forth. So take a look at page 273, equation 10.11. And there you'll see what angular frequency is equal to for a spring. It's the square root of k over m. Now you don't have to remember that one, but you do need to remember how omega and frequency are related and how frequency and period are related. And then remember the two basic ones. Period of a pendulum equals what? Period of a spring equals what? And that's the two equations that I will continue to review with you to get to you to make sure that you remember. So you will be okay by the end. And that's only for the multiple choice. For the free response, you have those equations at your disposal. Take a look at page 275 at the bottom, 10.13. That's all you need to know from here. Make sure you read that. In addition to that, there's one other little bit of thing. If you do a graph with f on the y-axis and displacement on the x for a spring, you should know that the slope is k, and you should know how to go from that graph to a proof of what the potential energy of a spring is. So you should be able to do that with a little bit of substitution. We did that in physics. If you don't know how to go from that graph to that answer, talk to me. I can show it to you in about 3 or 4 minutes. It's not too complicated. Take a look at page 279 for a pendulum. That information that's on there is for omega and for a simple pendulum for small angles. When they talk about the small angle approximation, it just means you're not taking the thing up to 45 degrees. Okay, so you're keeping it at a little small angles, like 3, 4, 5 degrees from equilibrium. So you take something, you swing it up. You don't usually use 10.15 for most of them. It's mainly 10.16. And we will, like I said, you'll have the period of a pendulum and a spring ingrained in your head by the end of this course. 10.5 and 10.6 and 10.7 are all things that if you're interested in, take a look at it. You had a reading assignment on 5 and 6 for just conceptual stuff in there. So if something there looks strange, read it. It's for the most part, it's self-explanatory. 10.8, stress, strain, and Hooke's law is not something we deal with. And 10.9 is just additional practice problems. At the end of this chapter on page 289 starts a review of all the equations. It might be a good idea to read over that as well. But remember, we didn't do equations from 10.7, so no equations from 10.7. That about wraps it up. If you have any questions on this section, because especially since it's new stuff, make sure you get it straightened away. The big thing is, angular frequency and knowing how to go from that to frequency. And of course, the other new thing is the displacement in radians. So that's two things that are for sure something you need to know from this chapter. That is all.